Thank you, and welcome to my Storage Day talk, Filling the Gap, LINBIT SDS in Amazon EKS. You likely know that EKS is AWS's managed Kubernetes offering, and maybe you're familiar with its benefits, but I'll go over them here just in case you're uninitiated. They will, out of the box, provide you with a managed Kubernetes, so that's a managed control plane, as well as a managed node group, so no worrying about updating your control nodes or the control plane or worrying about etcd backups or kubelet updates. They've got you covered. And they also integrate a lot of their services, their own services, into EKS. So we're talking about managed load balancers, elastic load balancers, as well as elastic block storage. They also provide you with out-of-the-box monitoring and logging through Amazon CloudWatch. This is often like the first thing you want to do on day 2 is get your monitoring and logging sorted. You've got it already day 0 with EKS. Access controls, not only for Kubernetes objects via kubectl, but also from within the cluster. So service accounts can go ahead and create those load balancers, create that elastic block storage, as well as workloads for you in Kubernetes. They also have the VPC networking covered. The VPC CNI is Calico based, so it's performant. That's what I use in my testing and in my clusters. So it's familiar as well. There's many more, too much to list. You can check out the EKS docs or marketing material for more on that. But with all these offerings, where does LINBIT fit into the EKS storage solution? So first you have to understand what offerings are available in the EKS. And the two main offerings are elastic block storage, or EBS, and the elastic file system, EFS. Elastic block storage is, like I said, block storage. It's the faster of the two options. It is a read-write once access mode, and it cannot be accessed across AZs. The elastic file system is file-based storage, so it's going to be a little slower, but it does allow you to read-write many. It allows that access mode for your PVs, and it does provide cross-AZ access. This is where LINSTOR fills the gap. LINSTOR is replicated block storage, so it's of that faster type of storage. It does allow only read-write once access, but it does enable access for block storage across AZs. So we're going to replicate your volume into multiple availability zones, and from there you can access it in whichever AZ you need to access it in. And how does LINSTOR work? Quite simply by layering block storage to enable features. So you see in the image on the right all the different layers that LINSTOR manages, but specifically in EKS, the layers managed from bottom to top are the EBS volumes themselves. That's the raw block storage that's going to comprise your storage pools. On top of that, we'll layer LVM or ZFS for volume provisioning. Typically, I'll use LVM thin because it's the features are there for snapshot shipping and whatnot. ZFS has those features as well. That's a user choice. I usually go with LVM just because I'm more familiar, a little slower to move on shiny new storage technology, but I know there's a lot of ZFS fans out there, so go ahead and use your preference. The most important layer is DRBD. That gets layered over top of LVM or ZFS. And DRBD is what's responsible for our synchronous replication between AZs. So without DRBD doing that synchronous replication, you would not be able to access your block storage in multiple AZs. There would be no failover story for multi-AZ failovers. So that's why I say that's the most important layer, not just because LINBIT also makes DRBD. Optionally, on top of DRBD, you can layer LUKS, VDO, or DM cache layers for encryption, deduplication, or caching, respectively. And then at the very top is the block transport layer, and we will use DRBD's diskless mode as our transport You can think of it like iSCSI or NVMe over Fabrics, where you're issuing raw block IOs over a network, but DRBD is more performant than iSCSI in tests that we've run, and yeah, it's baked right into the solution. So over the spring and summer of this year, I worked with members of the AWS DevOps team to create a reference architecture for highly available Jenkins deployments in EKS using LINSTOR. The typical deployment looks like this. And just to hit the points, we have a single region containing 3 AZs or more. I don't know of any AZs or regions rather that have less than 3 AZs, but if they're out there, you would not want to use that just because we can't achieve quorum on the storage layer, and that's very important to our solution. So when you're deploying this, you would want to make sure that your region has 3 or more AZs. Within that region, you're going to have 1 EKS worker in each AZ, and then you will attach EBS volumes to each worker. This is not just the root volume for the EKS worker, but an additional EBS volume for each worker. That's what LINSTOR is going to use for its storage pool. And then specific to the Jenkins deployment, we would deploy Jenkins running in any of the AZs accessing the LINSTOR persistent volume. And optionally, you can have a LINSTOR S3 remote configured for out-of-region snapshot shipping to use in your disaster recovery plans or strategies. And then, of course, an elastic load balancer redirecting users to the active AZ and the workload. Full documentation for this reference architecture is available on linbit.com, but you can also request it in chat, and I'm sure somebody will be able to get that to you. When deployed as defined in the reference architecture, what is the overhead? So I used FIO, the flexible IO generator. I think that's what it stands for. If not, I'm sorry if I'm wrong. And I ran that from a container within EKS using various different block sizes and IO patterns. And I ran that against the raw EBS volumes, as well as LINSTOR volumes replicated across 3 AZs in the US West 2 region. All that's on GP3 backed EBS volumes, but these are the results that I got. And we see that the read performance almost across the board is improved when using LINSTOR. Perhaps this is due to read balancing through DRBD or maybe IO merging from some other layer LINSTOR is managing. But either way, bigger numbers are always nicer to see. On the write tests, we see some overhead, specifically the very brutal random 4K write test, where LINSTOR is able to put up some respectable numbers. It's 78% of the throughput of the raw backing disk. So, that's even while replicating synchronously across all 3 AZs. I think that's pretty good and definitely a worthy trade-off for the high availability you get from that replication. So there's more of these tests, and more of these tests are in the full documentation. So if you're interested in seeing that, be sure to check out that document. What are the prerequisites for preparing to launch LINSTOR into EKS? The prereqs, these are all handled by EC2 launch templates, and I'll cover that in the demo portion of my presentation. So stay tuned for that. But the main details are that you're going to need to run DRBD9 within the EKS instance's kernel. And you can do that kind of one of 2 ways using the LINSTOR operator. You're either going to want to use a Red Hat or Ubuntu or SLES based EKS or EC2 image for your EKS instances. And if you do that, you can use the prepackaged DRBD kernel module that our operator ships with. Or, and what I would recommend doing, install the kernel headers during the bootstrapping process in that launch template that I'll show you. It's just going to be more robust if you do it this way. You don't have to worry about, what if LINBIT missed packaging for this specific kernel I'm about to update to. You'll always be able to compile successfully. So use that, and that's what I'll show in my demo. And then, as I mentioned before, you'll need those additional EBS volumes for the LINSTOR storage pools. You really just need only one, but for best performance, I recommend separating those two so you can have a data storage pool. That's where the persistent volumes for your workloads will actually store their data, and then a second storage pool that will be used for DRBD's metadata to track bitmaps, what blocks have been synced where, and that'll be on a separate EBS volume, so that way you don't have to kind of share throughput between your workloads, data, and DRBD's metadata rights. So yeah, and I'll cover all that in the demo. So let's jump into the demo, and I've not recorded a demo covering this yet, so pretty excited about it. Get this out there. It's been in some knowledge base articles and whatnot, but I'll give it to you live here. So let's switch to a shell. Just kidding. Let's switch to the EC2 dashboard. That's where we create the launch template. In the shell, we will be launching our EKS cluster and referencing the launch template we make. So if you've logged into your EC2 console, you'll see that you have a launch templates entry over here on the left. And I have one here that I use for various other demonstrations and whatnot, but we'll create a new launch template for the demo. And you're gonna want to give it a name, something that you'll remember what it was for, so that when you're tempted to delete it later, you either don't or know that it's safe to do. So I'll name mine LINBIT SDS demo, and I'll just give it a number for demo purposes. And you can add your tags so that it tags all the instances created here if you'd like, but I'm going to skip it. I will not select an application OS image, and I'm just going to use the Amazon Linux 2 image that EKS will default to. But this is where you would select that Ubuntu Red Hat SLES OS image if you wanted to use the prepackaged kernel modules from the LINSTOR operator. I'm going to go ahead and set a T3 medium instance type. That's a pretty small instance type. It's noteworthy to mention that LINSTOR doesn't need a lot, so when you're sizing out your instances, you can do that based on your application's needs and not worry too much about what LINSTOR needs. Now, if you start thinking about deploying instances with 100 plus terabytes worth of storage pool space, then maybe bump this up a little bit, because DRBD does need 32 megabytes per 1 terabyte to store its bitmaps for its peers. So that's a memory requirement to keep in mind. We don't need to specify a key pair, don't need to specify network settings. The storage section is the important section, and as I mentioned, we're going to create I'm going to create two different EBS volumes, so I can create two different storage pools so that I can separate DRBD's metadata from the persistent volume storage. And all these look good. I'm going to add a second volume, and this, we're only going to make it 4 gigabytes. This is going to be used for the metadata that I mentioned, and just like the memory requirements, it's about 32 megabytes per 1 terabyte per peer. So small will do. 4 gigabytes is as low as you can go in EC2. So that looks good, and then we'll scroll down, and this is the very last part, maybe the most important part, and it's going to be tough to copy and paste out of this video, but this information, like I said, is in our knowledge base, and we can also share it with you somewhere else if you're interested. But this is where we add the packages, the kernel develop packages for our specific kernel during the bootstrapping process of these EKS nodes. So yeah, don't skip this, otherwise you won't be able to compile DRBD, and that's going to be a problem. So so you see here, successfully created. There's the name of our launch template. There's the ID. I'm going to copy this, and I'm going to copy that ID because this is what you need to add to your either your EKS CTL configuration, your Terraform manifest, whatever you're using to deploy EKS. This is what you're going to have to reference to tell EKS to use this launch template to configure your EC2 instances for LINBIT. So now I'll switch to the shell, and I have a EKS CTL configuration here, and I'm going to paste in that launch template ID I copied earlier, and let me just show you that again. Very small configuration, nothing too special going on here. Just the version of Kubernetes that I would like to deploy into EKS, and then the launch template that we just created, and the size of the cluster. So 3 worker nodes spread across 3 AZs. EKS handles that distribution for you, so we can then use this to create our cluster, and we see that has kicked off. This generally takes about 20 minutes or less, so we'll just sit here together and watch it. I'm kidding. I'm just kidding. Through the magic of television, we're gonna let this go, and I'll skip ahead and catch up with you guys in a few minutes. Okay, so our EKS cluster is fully deployed. We can see we have ready nodes and nothing running aside the AWS specific stuff and control plane stuff. So I've gone ahead and prepared a LINSTOR operator values file, which corresponds with the settings we configured in our launch template. So specifically looking at the storage pools, we have that external metadata storage pool for DRBD's metadata on the smaller volume, and the LVM thin storage pool on the larger volume, which LINSTOR will use to store the PV data. And then some other options telling LINSTOR to use Kubernetes CRDs as its backend database, as opposed to etcd, which is the previous default. We're not going to use Stork, but we will use we will enable topology awareness on the CSI driver. That way LINSTOR and Kubernetes can make sure that volumes and workloads are strategically placed, meaning that they're on the same hosts for lowest latency access to persistent volumes from a workload. So with that defined, we can create the LINSTOR namespace, and we'll just do that with kubectl create namespace LINSTOR. Then we can go ahead and create our Kubernetes secret for accessing LINSTOR's image repository hosted by LINBIT. And I've hidden my credentials behind some environment variables here, but you can supply these however you see fit. And once we have that, we'll add the LINSTOR repository to our Helm charts repos. I already have that. I'm just going to make sure it's fully up to date. And from there, we can deploy LINSTOR. So we'll point Helm at our LINSTOR namespace, tell it to use the values we've defined. We're going to call it LINSTOR op. That's the release name, and this is the chart name to use. And we get some handy little tips on what to do next. You can follow these on your own time. I know that we're going to also do that and this. So This being, we're going to deploy the HA controller for LINSTOR into Kubernetes. That will make pod failovers using LINSTOR back storage a little faster than that 15-minute pod eviction timeout that Kubernetes defaults to. And then also the affinity controller. This regularly checks for replicas of a volume and updates node affinities on PVs so that Kubernetes knows our data can be accessed from new nodes that are added to the cluster later, or nodes that are assigned new replicas. Usually those node affinities are immutable, so you would not have that capability without this. And in EKS, worker nodes come and go, so you want to make sure that you use that. These require less options. I don't actually change any of the default settings here, so I'm just going to deploy it in a similar way to the operator into the LINSTOR namespace, call it LINSTOR HA controller, and that's the chart name. It does spit out some helpful information about what you'd want to set in your storage classes. And I have set these in the storage classes I'll use later. But then also, if you want to opt out of the HA controller's evictions, you can label a workload with that annotation, and LINSTOR will skip over your pod and not fail it over should it think it wants to. So that was the HA controller. Here's the affinity controller to keep those node affinities up to date. Again, I don't change any of the default options, and it will automatically find the correct controller and attach to that. With all that defined, the next thing you would do is create your storage classes. I've pre-configured these. We're just going to look at this last one here as they're identical. Besides the auto place count, I usually create one with 3 replicas, 2 replicas, and then 1 replica. But so we just have to look, and I use the same options for all. So we'll just look at this last one. We're going to use that LVM thin access or storage pool. We're going to allow remote access, volume access to false, making sure that we do not disklessly attach to our replicas from our workers, and we're going to do all our IOs to a local replica. This just helps with performance. And then these are the options that we want to set with the HA controller configured, and these are some generic or performance-oriented configurations specific to DRBD that I usually configure. And also this is the property that tells LINSTOR to use our secondary storage pool as the DRBD meta pool. And volume binding mode, wait for first consumer, ensures that CSI topology aware placement of volumes and workloads ensures that it works correctly. You want to wait for the workload to be scheduled before we create the replicas. So those defined, we can apply them to our cluster. I see the 3 get deployed, and we should have our LINSTOR cluster up by now. Yep, we're all good. So I will cancel that watch. And now that it's fully deployed, we could create a demo stateful set, or just create PVs and see them get defined within LINSTOR. I've done a lot of work with Jenkins through the AWS DevOps team collaboration, so I'll go ahead and step through that quickly, as it's pretty easy to follow along with. So it's very similar steps to how the LINSTOR operator is deployed, adding the repo for Jenkins, preparing a values file. We're telling Jenkins to use the storage class that is replicated 3 ways. Only create a 2 gig volume, and we're going to put a load balancer up in front of it. This will use the service integration that EKS offers with its ELB load balancer. So we'll get a nice load balancer that directs our users to the correct node. And these are some of the requirements that were recently added to the Jenkins deployments Helm charts and we need to include those. So operation or operator values defined, we create the deployment in the Jenkins namespace, and we get some helpful output here. And this is how you would retrieve your admin password, and this is how you would retrieve your Jenkins URL. Because this is a demo, I'm not going to show you those things, but I have another terminal that will show me those things. So let's make sure that we're actually deployed. The pod's initializing, so we'll have to wait for that before we can access it. And we see it's almost running. Let me see if I can get this URL in my browser. And there it is. So I'll switch over to it. This is my Jenkins deployment. I'll log in using the username and password it showed me. Never remember. And real quick, I'll just create a job just to show us failing over and preserving our data. Demo or something. You would probably pick some more useful entries for your fields here, and we'll just execute a simple shell command. I'll copy paste what I got here. So we're just going to create a file from urandom named job name. That's a variable name in Jenkins, and we're going to take a SHA-1 sum so that we make sure we're seeing this. We're not seeing false data or pre-recorded data, whatever. And let's say archive the artifacts, and that would be this job name.dump. So I'll copy that from up here, and we'll save, and we'll build now, and we should see the build kick off. Here we go. And I chose 10 megs, so it shouldn't take too long, but demo time I know feels like forever. So bear with me there. Now that we see it going, we can jump over, check out the console output. See it succeeding. It's archiving the dump right now. Finished. There's our SHA-1. We can check it out. F09. C2C. We just remember the beginning and the end. And now we can jump back to our shell, and let's see where our pod is running and watch our node states. So we see we've got it running on this IP 192.168.94141. I'll jump back to my EC2 dashboard and find that instance. That's this guy. Got lucky, 94141. And we're going to terminate that guy. Just delete the whole worker node. And we'll jump back to Jenkins, and if we refresh, we should see that we're down temporarily. I can see a pinwheel spinning. We haven't timed out quite yet. We should see that timeout soon. But back in my shell, we can watch, or we can already see that the scheduling has been disabled for this worker node, and soon we'll see EKS kick that node out of the cluster, and we'll see the pod fail over and see that it will, oh, it just moved. So now it's on IP 192.168.19.143. And let's jump back to the dashboard. Oh, we'll wait for this pending status to move to running. We see the node I terminated was kicked out of the cluster, replaced by a new node. We see the pod status is now running. We didn't have to wait that full 15-minute timeout. And now if I jump back to my dashboard and reload this page, I should see that eventually this wakes back up. There we go. We're back in our status page of our project. Yeah, and there we go. I see, you know, there's our artifact that we saved from the last output. We still have our persistent data. I think I can even look at this build, and we don't have to we can just check that the SHA sum is still there. F09 C2C. So we didn't lose any data. Barely any downtime for this, you know, singleton workload running in EKS on top of LINSTOR storage. Yeah, and that is how LINBIT fills the gap in EKS's storage offerings, allowing for block access or block device HA inside of EKS across availability zones. Something that EBS alone cannot do. EFS can do, but without the performance necessary for some types of workloads. So at this point, you've seen it, and if you'd like that documentation, we can get it to you. But if you have any questions for me now, we'll open up the floor to QA.